Now we're going to look at linear maps as matrix multiplication. So based on this idea that we looked at in the last clip about how every n-dimensional vector space is basically Fn, and that the space of linear maps is basically Fmn, then matrix multiplication is just a way of writing down a linear map. So let's let V1 through Vn be a basis for V. And let's take some element V of our vector space. Then, since we have this basis, we can represent V in terms of this basis. C1 V1 plus up through Cn Vn for some choice of coefficients Ck from our scalar field. And then the matrix of V in terms of this basis is just the column vector of those coefficients. So the matrix for V is C1 through Cn. So now look at how we can use this. So note that if we just take an example for the standard basis, V1 through V and of V. Sorry. Let's do this specifically for R4. Then let's look at A times V2, where A looks like, and let me make something up. So we've got 3, minus 1, 1, 2, 0, 4, 7, 2, 1, 2, minus 2, 4, 5, 8, 8, minus 1. Okay, that's going to be our A. And then V2, the second standard basis vector is 0, 1, 0, 0. And so you might ask, okay, where does A map this basis vector? And when you do the multiplication, and you probably noticed this from your previous linear algebra class, you just get exactly these guys, right? Because there's one here. When you do a dot product, it's going to catch this one, and then on the next round, when you do the dot product for the second row, it's going to get this one, and so forth. And so you just end up with minus 1, 4, 2, 8. And so this guy is the second column vector. Okay, so it turns out that this holds true in general as well. And so that's the content of the next proposition. So this is 364. If we take a linear transform from V to W, and an arbitrary basis of V, then the kth column of the matrix of T in this basis is the matrix of the vector tvk. And I should point out in the book, there's a rather serious typo. This T is missing. So it just says MVK. So this is on the top of page 85, there's about 3 instances of this typo. By the time it gets to the midpoint of the page, things are going okay again. But that T is missing in 3 places, which confused the heck out of me the first time I read the book. So let's see. So then we will use that idea to show that for a linear map from V to K and an element of the domain, that if we look at M applied to TV, this is actually the same thing as the matrix of T times the matrix of V. So that's matrix multiplication. Okay, and so the proof for this one is that if V1 through Vn is our basis, and we write V in terms of this basis, then TV is going to look like the linear combination of the TVJs, just because we can use linearity to sort of push the T through. And then the matrix of TV is going to be, and I'm going to substitute in that thing that I wrote in the previous line. So just take this guy here and squeeze it in there. So we have whoa, something very interesting just happened with my drawing tool here. Okay, so then we're going to have the sum of CJ, T, VJ. And now we've seen before that M is linear, so I can push the M through. So I have CJ and then matrix of T, VJ. So this is by linearity of M. And then let's see now, we've got this proposition just a couple lines up that tells us that this is going to be that M of TVJ is the jth column of MT. So this is by 364, which we did just above. And then this is by definition the matrix times the product of the 2 matrices, where we do matrix multiplication, and that's by 352. And we're done.